Yeah, thank you. Yeah, so like any good story, or like any good research, this started over a beer about a year ago. I was at a different conference actually on software security, and we're talking about symbolic execution, and I'll get a little bit into what that means if you don't know what it is. And one of the things is with symbolic execution, you cannot analyze crypto, was the thesis, because crypto is too complicated. But I was thinking, well, I'll leave that as a cliffhanger for somewhere in the middle of my presentation. So my mother always told me don't put mathematical equations on your slide, but she never talked about assembly. So let's start here. So I first want to explain just a few concepts to you guys. So I want to make sure that you have a rough understanding what symbolic execution is. I want to have a rough understanding, or want you to have a rough understanding of what fault injection and differential fault analysis is. And there will also be a little detour on Bitsliced crypto. And then I hope you might still understand what we've actually been doing. So let's get started. I hope you're familiar with concrete execution, which is what any microprocessor does. So you give it some registers, you give it some instructions, the machines turn, and then you get some output. So for instance, we have a register 1 with the value BE, a register 2 with the value 8. We say, please move the value of R2 into R1, then add 10 to that, and then this is the result. Very straightforward. When you talk about symbolic execution, this is actually something that no microprocessor natively does. You can have some registers or some parts of the memory be symbolic, which means that you actually don't know what the value is. So you can say, I have a register 1, which I don't know what the value is. We'll call it symbolic. Then we have a register 2, which is 8. And then I say, again, move register 2 into 1. So at that point, we know that it's actually... wait, did I make a mistake in my slides here?
Yeah, because this is the same as the previous one.
Yeah, you're right.
Here,
Yeah, it should have been the other way around. Yeah. That's my problem here. Well, I'll debug that for the next session. But thanks for your patience. So pretend that this is the other way around. And then we have, at the end, instead of a concrete value, we actually have an expression. So we know now that R1 equals R2 plus some concrete value. And R2 is still 8. So really what you need to remember here is that symbolic execution turns programs into equations. Yes, thank you. I was testing you. I'm going to make it a little bit more complicated, and obviously I made the same mistake here. But I'm going to introduce one complication of symbolic execution, which is that it will not turn your program to one equation. It can actually turn it into many equations, depending on some conditions. So here's a little bit of assembly that basically does the same as before. But now there's an if statement that says if this register is some value, then I jump to A, in which case I set R3 to 1. If it's not the case, then I set R3 to 0, and I also jump to B. So now my program actually turns into two equations, depending on my input. So now if I have a certain condition, then R3 will be 0. If I have another condition, then R3 will be 1. So all good so far. There's a few problems that you get because you can actually get a lot of these equations when your program grows. We're going to, for today, ignore that problem a little bit until we run into it. But for now, keep in mind that when you're doing symbolic execution, you have some program. It turns into a set of equations, and on those equations you can run a solver. So you can actually say, once you have these equations, if I want R3 to be 1, give me the values for R1 that would satisfy that. So you can sort of turn programs around. You can say, hey, I want to arrive at this state. Give me the inputs for that. And this is actually really interesting for security. I don't know how many of you do code reviews or things of that nature, but you often look at snippets of a program, and at some point you find, hey, this could be an issue if the input to this program is X. But often, like, going backwards in your mind through the execution of some piece of source is pretty hard. So these kind of things really help you there. So that's how I first got interested in symbolic solvers. But that property I will not use today. I will actually be using the equations and the solver part. So that's on symbolic execution. Now I also have to talk about fault injection. So when I do fault injection, I'm actually going to manipulate what a program is doing while it's executing. And there's a few things that can happen. I want to try to, for instance, skip an instruction, or I want to change some register value. And this is possible with a few techniques that I'll highlight in a second. But for now, just for your mental picture, assume that when I introduce a fault, I'm actually skipping an instruction. So with these powers, let's say that we're back to this state, and I hope I don't have a mistake in this slide as well. So we have one register value which is BE, and we have another one which is 8. But now we skip this whole instruction and continue executing. We add 10 to R1, and now all of a sudden we see the output is CE. So we've actually caused a fault in this device. Now you think, why would I do this? What does CE mean? In this example, your program probably crashes. But let's say that this is a password check, or this is a check during secure boot of a device. If I can skip the conditional branch that decides whether my passcode is correct or not, or whether my firmware image is signed or not, this is actually a huge security problem. So that's why in security, and especially in hardware security, we're interested in these kind of properties, because we can do things like this. So we have a piece of hardware, and that means we actually have physical control on its environment. And physical control in terms of hardware can mean I can control the power supply to a chip. If it has an external clock, I may be able to control the clock to the chip. I control the electromagnetic fields around the chip, so I can inject pulses. Or if you look at this picture to the right, if I decap the chip, I can actually hit it with a laser beam. Now all these techniques, they've proven to cause faults on a chip. And faults obviously give the security problems that I talked about before. What you're seeing on the picture left is actually a clock glitch. So normally a clock is just this block wave, but there's all these weird kind of patterns in there that we've injected. And that can cause a chip to also malfunction. Recently, there have actually been some quite interesting publications, because fault injection has really been in the space of hardware attacks. So we're controlling the environment, and therefore we're causing faults. However, there's two specific instances that I would like to highlight, where software controls enough about the environment that it actually can cause faults on the device it's running on. One of these examples, and this afternoon there's a much better presentation fully devoted to DRAMmer type attacks. But it's DRAMmer. The basic idea is that if you have a DRAM memory that needs to be refreshed every now and then, otherwise it loses its charge and its data. And you can interfere with this reset cycle in such a way that if you start writing really rapidly certain areas of that DRAM, so DRAM is laid out in rows, and you write 2 rows besides what's called a victim row, you can actually influence the data in that victim row before the refresh happens. So you're essentially flipping bits in DRAM, and you can trigger this from software. So this is actually a fault injection. It's just you can cause it from software. And really the the big impact of this is that you can scale it much easier if you're an attacker, right? I no longer need physical presence to the device, which I would need in the hardware scenario. Another recent example is that of clock screw. That's spelled CLK and then just screw like in corkscrew. Was presented, I believe, last month at Usenix. And this one is pretty cool as well. So what they took is a mobile phone, like a Nexus. And I don't know if you guys are familiar with trusted execution environments, but basically you have Android, which you're familiar with. Next to Android is another operating system, which is more or less hidden. I mean, people know it's there, obviously, but it's hidden from full access from the Android side into something called normal world and secure world, enforced by ARM trust zone, in case that means anything to you. So what they found is that even though when you load an application into this trusted OS, it's got all kinds of signature verification happening, so not everybody can just load arbitrary code there. It always needs to be signed. But they found that from normal world, you can actually access the PMIC, it's called, is the power management IC. And what you can also control from normal world is the CPU frequency of each of the cores. Now, these two triggers, you may have, these two triggers give you a lot to play with, especially since what they found in their research is that you can push the voltages out of the normal operating ranges. So you can actually control the environment in such a way that your chip doesn't get enough voltage. So what they basically do is they push the voltage down to the lowest level where the thing still runs, and then they bump up the CPU frequency of one of the CPUs. And the effect is it starts making faults. Now, it's actually a mind-blowing paper. They bring in so many attack techniques, but what they basically end up doing is they are able to trigger a fault right at the moment when the RSA verification is happening. They don't, and this is something I still want to ask the authors, they're not actually targeting the conditional branch that says this TA is signed correctly, yes or no. They are targeting the RSA computation, but they're creating a fault which is predictable, and they're able to calculate, I don't know, do you guys know how RSA roughly works? Yeah. The RSA, you need to make sure that the key that you're using is the modulus that you're using is a multiplication of two big primes. So they actually inject a fault somewhere during the computation where effectively the modulus becomes factorizable. And they do this in a predictable way, so they can calculate what actually the private key is that corresponds to the faulted public key, and then they can sign their own trusted applications. So they use much more techniques like triggering, using side channels and everything. It's pretty cool work, so you should look it up. But in the end, what they're capable of doing is just load arbitrary trusted applications into secure world by causing this software-based glitch. So fault injection is interesting field of study. But yeah, this stuff scales, right? This is purely software-based. So now that I've talked about two things, symbolic execution, I've talked about faults, I'm going to talk about a different kind of fault. And it's a fault that you introduce while you're doing a cryptographic algorithm. So what you see here is the tail end of a DES encryption. So DES is a Feistel scheme, which has this very specific kind of repeated structure that you see. And what I'm going to talk about is what happens if I flip a few bits right when it's there. So the cool thing about flipping bits here is that you can actually see this effect in the output directly. because these bits actually go down here and it goes through an XOR, but you can see exactly kind of which bits are flipped, because there's no permutation or anything happening right there, so you know exactly which bits you flipped. What also is happening, and this is kind of the intuitive idea behind differential fault analysis, is that if I glitch this, there's only a small part of the key being added. We only have one round of the algorithm left. So you can actually work out by which fault you have. Let me go to. And the reason why I'm hand waving here is this is like an hour-long lecture if you're going to want to understand all the details. What I'm trying to make you understand is you can track this fault through an f function. This is what the f function looks like. And you can find out exactly which bit from the output you have. You can see which bit in an Sbox was affected. And if you look here, you have one of these Sboxes. It actually has an input of 6 bits, which corresponds to exactly 6 bits of a key. So you can, just by looking at what output you get of a faulted cipher, you can identify which Sboxes have been changed. But you can also see the change, obviously. And by combining the fact that there's some fault here and the change that you see at the output of the Sbox, you can reduce the number of key values that actually fit both equations, that fit the correct output and the incorrect output. So the way we usually do this is we make a table. So we calculate actually what the XOR distance is between the two Sboxes. So these are 4-bit outputs. So the XOR is maximum 4 bits. And that's something we can observe from the output. So we can just say, hey, the XOR is 0xe. We can just look up in this table all the values where the XOR is E. And that gives us a few key candidates, so 2 and A and 21 and 24 and 29 and 2C. So just by introducing this one fault, I can reduce my key space for those 6 key bits from 64 possibilities to, in this case, 6. So all I need to do is do this attack a couple times in a randomized way, and this key space will keep on reducing until at some point there will be only one key left. So that's really the general idea. If we take it a little bit more modern, we can look at how this works out on AES. So what you see here is the tail end of AES, so round 9 and round 10. And let's say we introduce a fault right before this operation. It's called a mix column. So AES has a state matrix which is 4 by 4 bytes. It's 16 bytes. And let's assume we flip one of these bytes. So here we have the state matrix before. We do a fault injection. We flip one byte. So instead of A, the value becomes X for whatever X is. We don't necessarily know that, but we know that that byte is faulted, or we assume so. So now we can just calculate through the remainder of the cipher and see how this faulted value of X actually propagates throughout the cipher. So this is just a matter of applying the formulas of AES. What you see here is that X appears here, X appears here, here, and here. Normally that would have been A, but we now have a faulted one. We continue going, so we have a key addition here, so we add the XOR the key at the end. Then we have an Sbox, so we do the Sbox over all of this. Then we have a shift row, which is just not changing the formula, it's just their position. And finally we XOR another key onto it, and this is actually, the output of this operation is actually what's visible to us as an attacker. So we glitch 1 byte here, and we see actually 4 bytes change. I really should have listened to my mother. Anyway, In normal AES, the equation looks something like this. And remember again, the attacker can observe outputs. So he can run AES one time without faulting it, so he knows what O looks like. He can fault it, and then you see the X appear in the equation here, and you get some other output. And the nice thing is if you XOR these two equations, so I do that here, then these two key bytes cancel out. And I can actually, by some rewriting, I can rewrite this as the Sbox over a certain byte XOR 2Z XOR the same Y again. And if I get sufficient number of these equations, then I click solve this for Z, and if once I know Z, I can solve it for K. Again, this is many pages if you want to work out the details, but the idea is I glitch some byte, I get some differences in the output, I manually figure out how these equations work, and then try to solve them. So what really happens here is we have some faulted cipher, we have some PhDs that start making equations based on some fault model, and then you can rewrite those solutions in order to find the key. And really the problem that I had with this is that I'm too stupid to come up with these kind of things. So I want to have something that I can use. So this is the insight that I had over this beer about a year ago. So first of all, we have this tool of symbolic execution. So I can take a program, turn it into a set of equations, and then we can solve them. This is pretty much automatic. You just load it into an engine and it will give you these equations. Differential fault analysis takes a faulted cipher, you have to manually study it, study the fault model, you have to rewrite it, and you have to come up with how to solve it. So I actually want to combine the best of these two worlds. So this is the idea. So I want to take a faulted cipher, so I inject some fault somewhere, but then I want to use symbolic execution to figure out the equations for me and also figure out what the key is for me. So that's what we set out to try. So in our first experiments, what you basically do is you take this tail end of a cipher, in this case AES, and you run it through a symbolic engine. And what you do is you make some of these inputs, you make them symbolic. So I make the state symbolic, because normally at the end of round 9, as an attacker who doesn't know the key, you have no idea what that intermediate state is. Because to know that, you need to know the key. So we make it just symbolic. Another thing we make symbolic is the fault itself. Because we often don't know really, I mean, a few slides back I said I'm going to change this A into an X by faulting it. Usually you don't know what's happening. So you may just, basically with faults, you're just hitting the thing with a hammer and then you're hoping for it to, land somewhere where it's useful for you. But you don't always have that control of like, I want to hit this precisely. So I'm just going to make my fault symbolic as well. Let's see what happens. And then there's the key, which obviously I don't know. So I make that symbolic as well. So the outcome of this, if I run it through a symbolic solver, is basically I run the partial AES using this symbolic state and a key. And then I get a symbolic output, which is basically an equation that involves the state and the key and the output and relates them together. And now I'm going to start faulting this. So instead of giving it the same state again, I XOR some kind of fault on top of it. And this fault is different for every time I create another run. So the state is constant, the key is constant, the fault is different for every time I do this. So I build up more and more and more equations. And at the end, I just say solve for key. That's how stupid I like to be. So obviously this failed miserably. Well, maybe not obviously, because otherwise I wouldn't have done this experiment, but it failed miserably. So we had to poke around a bit and figure out why is this not working. So this is going back to my earlier statement on symbolic execution and how it can end up with a set of equations, even for one program. And one of the things that symbolic solvers really choke on are these kind of expressions, and I'll explain why that is. In this case, imagine that the input value is a symbolic variable, so the solver doesn't know what it is. So how do you implement a lookup table in memory? Well, basically it becomes an expression that says if the input is 0, then out is 63. Else, if the input is 1, then the output is yada 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 yada, all the way to 256. And you do this for 16 Sboxes and you run it through a mixed columns. At that point, I gave up. So basically you start the program and the symbolic engine is just chugging and chugging and chugging, and then it runs out of memory. And tried all kinds of things until we realized this is not the way to go. So I'm going to take another detour. Who of you guys have heard of bit slicing in crypto? Oh, good. You're learning so much today. Let's say I have some crypto operation that takes in 4 bits and XORs it with another 4 bits and produces some value X. This may be some elementary operation in a crypto algorithm. And typically in software you would have 2 variables and you XOR them together and you get X. Now I'm going to do something that superficially looks really stupid, but I'm going to implement that as this. So instead of having one variable X that's 4 bits wide, let's say that 4 is the machine word size. I'm going to make 4 equations out of them, each of them containing 1 bit of X. So now I have 4 variables, and instead of having the values kind of horizontal next to each other, I'm going to put them vertical next to each other. So the output is still the same. The difference is I'm now using 4 times the number of variables. This is what bit slicing does, and it's silly unless you do also this. What you see here are the original values in this first column. But the cool thing is, actually let's assume that this is an 8-bit wide CPU. I can actually do 8 XORs pretty much in parallel if I represent things in this way. So let's say that I, instead of wanting to run 1 AES, I want to run 8 of them in parallel because I'm brute forcing something, or I'm running a, who knows what, CBC encryption, counter mode encryption or something like that. So by kind of transposing your whole problem, you can now run 8 operations of these 4 bits in parallel. And I'm still using only 4 variables. So this is used a lot in software crypto to speed up things like brute forcing, etc. Because you're using all the bits in your registers to actually be able to calculate crypto. Now, there's one kind of downside to this, and that's the downside I'm actually going to be using, is when you use parallelism this way, it works quite well with Boolean operations like AND, OR, NOT, XOR. But you can't really do a table lookup. I can't tell the computer to look at this value and then replace it in those 4 registers with the. I don't think there's any CISC machine that does something like that. So as a consequence of that limitation, there are all kinds of implementations out there for AES, for DES, for you name it, that are bit sliced, that are not using any lookup tables. And that's exactly what I wanted. Because lookup tables hurt when you're doing symbolic execution. Boolean stuff, solver loves it. So this is what the LUT-based AES Sbox looks like. This is what the bit sliced implementation looks like. So it's slightly more complex, so it's not intuitive directly that this will help, but we decided to give it a go, and it actually turned out to work. Just for your reference, this is what the Sboxes look like for DES, so it gets even worse. Has mainly to do with the fact that you have 8 different Sboxes in DES. So you basically have 8 of these functions, and I had to do a little bit of search and replace to make it fit on one slide. But you can just pull this stuff off the internet if you just look for bit sliced crypto. So now, instead of using these vanilla implementations with lookup tables, we took the Bitsliced implementation. And now let's see if my sacrifices to the demo gods have paid off. And you probably can't read this, can you? Oh, wow. So this is using Anger, which is a symbolic engine and solver. And it basically implements what I just said. So in this case, it's the DES example. And what it does is it creates, I'll pause it for 1 second. So it creates a faulted left and a faulted right side of the algorithm. It runs it through the symbolic solver, and then it generates one more equation. And it just keeps on generating equations until the solver says, I can now solve it for one specific key. Because once the solver says, well, this set of equations can be solved for the key, and then you're done. So you can see it's doing some administration that says finding the key. If it then continues, then it wasn't the right key. So I'm going to just let it pop a little bit. And then fingers crossed, at some point it should say, I found the key. Yeah, actually that's what I wanted to see. So here it says I did 0-bit flips on the left side, I did 16-bit flips on the right, and I'll get to that in a second. It needed 4 faults to extract the complete key, and it took 50 seconds. So this is basically just running in a loop because it's doing different experiments. So this is at the level that I like it. I just put in a program, I just let it run for a while, and I say solve for key. So that was very happy to see that at least that theory worked out. I'll cancel it, otherwise. No, we'll let it cancel in the background while it's draining my battery. Oops. Oh, there we go. Yeah. So it worked for that little toy example, but now we actually get something to play with, because one of the things I haven't really touched upon yet is fault models. And that's basically, if you inject a fault, if you basically hit it with a hammer, what's the fault that gets generated on the chip? We usually don't know, and it's kind of hard to experiment with. But now we have something nice that we can play with. So here are a few different examples of fault models. So if this is the original value that I had, one fault model is, for instance, clear a byte to zeros. So every time we hit it in a certain way, something gets cleared to 0. That's one fault model. The other fault model might be I invert all the bits. Or yet another one is some random bits get flipped. And it's interesting to study the relation between the kind of fault that you introduce and how long it takes to get the key out. So how many attempts do you need to do to actually get there? So we did that in this rather confusing graph. Let's just look first at the line with the downwards pointing arrows. So what we're varying here is 2 things. So in DES you have this left-hand side and you have this right-hand side. And we're varying the number of bit flips that we have in there. So for this blue line, we're basically saying the left-hand side we do 0-bit flips. And the right-hand side we vary according to this axis. And then here you see how many attempts it requires on average to get the key out. And what you see is if you flip 1 bit on the right, it takes about 14 faults to actually get the key out. But in the optimum side here at 16 bit flips, on average it's about 5 to 6 faults to get the full key out. What we also notice, which is logical if you think about it, if we increase the faults on the left-hand side, it actually doesn't help us. We're not learning anything new about the key if we inject faults on the left-hand side. That's because the left-hand side actually doesn't go through a key addition anymore. So all we're doing is kind of complicating the analysis when we increase the number of bit flips on the left. Whereas if we do it on the right, we're actually gaining information in those equations. But the nice thing again is I didn't have to think about how to deal with faults in the left-hand side and how to compensate for it, because my solver just does that for me. Now, this isn't all magic. The reason why, for instance, you don't see deltas larger than 2 here is once I get to deltas 3, 4, 5, it becomes extremely slow. These things don't add information, so the number of faults I need to inject is much larger. But one thing we really noticed is that the number of equations kind of exponentially pushes the computation time up. So the solver becomes really, really slow at some point. So on the right-hand side, it's fine, because that's giving us information. Left-hand side, it's just noise. I have to watch the time a little bit here. I'll actually skip this. One of the things we did is we also tested on an actual device, kind of a test device we have internally, just to see if we fold something, how many bits are actually flipped. And this distribution shows usually 16 bits or 4 bits are flipped, which makes sense in an AES, because 16-bit flips is the average number of bits that flip if you corrupt the 32-bit value. Same with 4 bits for an 8-bit value, which are kind of natural sizes in AES. These are the results for AES. So we see if we flip a certain number of bits, so 1, 2, 3, or 4, we actually see that the number of faults we needed to get the full key out didn't vary that much. So we have 2.4, 2.3, 2. So generally, we only need about 2 faults to get the key out. I have to say that this is the not the full AES key, but the key for that particular 4 bytes of mixed column that you have. So, but you can run this in parallel, so you can glitch multiple columns in parallel. For the only problem we here again have is computational complexity. So, you know, this is anywhere between 1 minute, 10 seconds. Once the deltas go up, DNF means do not finish, which basically means we ran out of patience and we killed the process. But the time really explodes there. So, concluding, we're on par, or we have fewer faults needed than what's known in DFA literature. So that was really a nice gain. Another thing is that we can try arbitrary ciphers. So as long as I have a software implementation of the thing, I run it through the solver and I have another DFA attack. So I don't need somebody with a big brain to come and study all this stuff. I just need the implementation. Similar with fault models, I'm not assuming very much. I'm just assuming my state gets corrupted and let the solver figure out what fault model that is. With a few caveats, so we need these lookup table free ciphers. Faults must also fit the model. So, for instance, if I can put in a fault model that says I only flip this particular bit in AES. It'll work. But if I flip other bits, then the solver says I can't, this doesn't fit my model of the world. So you get something called unsatisfiable. So that's still an issue. And yeah, the performance significantly decreases with the number of equations. Now, we have some ideas for the future. So we can extend this to unknown ciphers, or maybe even something like white box crypto. Where with, for instance, an output encoding or something that's unknown. Problem is still these things make use of lookup tables a lot. So you would have to find some kind of way to convert lookup tables into Boolean arithmetic. Well, there's methods for that. I just haven't seen it applied kind of automatically yet on ciphers of this nature. And we think we can use like bucketing of a few faults and maybe statistics on top of that to avoid the unsats and also the slowness. So I got to thank a few people, my colleagues Kees, Bart, Raj, and Sergio and Panasaya for helping out on this research, and also the guys who made the Anger Symbolic engine. That's an extreme amount of work, so grateful to them as well. I'll be releasing the code and the paper at some point, so I'll announce it on my Twitter when that day has come. For now, I think we have 4 minutes for questions.
Thank you for the talk. I assume that the fault you injected are on the last rounds of the ciphers. Do you think, since it's automated, you can apply this for middle rounds and stuff that we can't actually solve easily?
Potentially. So we know that if you do it in the first round, it's basically the same as inverting the entire cipher. So you cannot do that. But how far you can stretch it into the middle rounds, we haven't actually tried that. I would expect that your equations get maybe also exponentially more complex. So theoretically it works, but in practice, whether it's computationally still feasible, I don't know. But it's something to try. Yeah. Thanks.
Hi. So you were saying with the lookup tables for the Sboxes, you're having problems with the Symbolic engine. Would it help at all to not implement the lookup tables as Sboxes as lookup tables, but as the mathematical implementation with the Galois field multiplication and so, or does that introduce something else you have to worry about?
That's a good question. So there's a few ways to represent these tables, right? So one of them is just to have a lookup table. The other one is the Bitsliced crypto that we used. Other ones is, especially in AES, they have a certain mathematical structure underlying it. I think we tried that at some point. The problem was that there's a for loop in there somewhere for one of the inversion functions, which actually doesn't have a constant number of rounds.
Okay.
And then you end up with the similar problem again, that the symbolic engine therefore doesn't know how many rounds it has if there's a symbolic input. And then you get all these branches. So every time at the end of the cycle, you get one extra path, and it also exploded.
Okay.
So, yeah, and I think it's one of the inversions in there. This is work that Kees did, so I don't know all the details, but I know it exploded in our faces as well. Okay. Thanks. Good question.
One last question.
Yep.
Have you tried this for ciphers with any other kind of structure than like a Feistel structure or something like that? Like sponge-based ciphers or something in that direction? Does that affect the...
So we only tried it on AES and DES. So AES is also not a Feistel, but yeah, I haven't specifically tried anything else. I would say as long as there's... let's say a lot of the key material is still used in the last part of the cipher, I think you should be okay with just any kind of implementation if it's lot-free. But I haven't tried it, so I don't know for sure.
Thanks.
Yep. All right, I think that was the last question, right? So thanks, everyone.
Thanks, Jasper. Thank you.